Okay, so we're very happy to have Fedor Pakhomov here at MOPA to speak on how to escape Tennenbaum's theorem. So go ahead, Fedor.
Okay, yeah. So thank you for introduction and thank you for inviting me to the seminar. Okay, so yeah, so today we'll be talking about certain result around Tennenbaum theorem, and namely, so of course, Tennenbaum theorem tells us that the only computable model of Peano arithmetic is the standard model. And now, today we'll be talking about certain variation on this, where in fact there will be a theory that will have a lot of non-standard computable models. Okay, so this is what I will be talking about today. So let me start. Yeah. Yeah. So okay. So Tennenbaum theorem tells us. That there are no, the only computable model of Peano arithmetic is the standard model. So yeah, to kind of remind you the basic definitions. So model is called computable if its domain is a decidable set of natural numbers, and all in the interpretations of all predicate and functional symbols of the model are computable. So in other words, so like if you have an array predicate, then it should its interpretation should be a decidable set, and interpretation of any function should be a computable function. Okay, and of course, like this definition is appropriate for models in final signature. In general, probably it's not the best definition, but anyway, it wouldn't matter today, since I will only work with theories with final signature. Okay. 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 So conceptually, the problem that I want to look at is the following. So of course, we have Peano arithmetic, and why Peano arithmetic is good is because it allows us to formalize reasoning about finite objects by induction. Okay, but then there is, at least if you look at Peano arithmetic from this perspective, so not necessarily this theory of natural numbers, but rather like something more broad. So the theory that allows us to just kind of reason about finite objects. Then the particular choice of signatures seems a bit arbitrary. So of course, one could formulate theories in somewhat slightly different signatures that would essentially do the same thing. Yeah, in particular, one could switch from the notion of natural number to the notion of hereditarily finite set, and essentially be as good as the notion of natural numbers. So one could still formulate or formalize all this reasoning about finite objects, but now just using this hereditary finite set as kind of basic finite object rather than natural number. Yeah. So this essentially would be kind of the same thing. And okay, so basically this kind of idea of two theories essentially talking about the same things, but in different terms, is captured. Okay, there's actually several ways how one could capture this, but like probably a kind of this most strict version of this would be the notion of definitional equivalence. So we say that two theories are definitionally equivalent if they could be extended to a joint definitional extension. So this basically means, so you kind of so you have kind of like two theories. So we assume that the signatures are disjoint, and then you could define in one theory some additional predicates, and they will give you other theory, and vice versa. And what should be happening is basically when you kind of extending to the language, you have both the elements of the signature of theory T and of the signature of theory U. then basically this resulting theory should be definition extension of both T and U. So essentially, what in the practice we could go back and forth between signature of T and U. Yeah. So. Yeah, so essentially typical situation is with the definition equivalency, then basically you kind of just have some choice of basic functions in the signature. So for example, so for example, if you're talking about linear order, so you could choose as your basic notion this predicate less than, or you could choose as your basic notion the predicate less than or equal to. And basically then you could have these two theories, one axiomatizing total order in terms of like strict comparison relation, and other axiomatizing total order in terms of non-strict comparison relation. And of course, the resulting series will be definitionally equivalent. So because you go back and forth between strict less than and non-strict less than. So that's basically what definitional equivalence is. Okay, so
Fedor, can I ask here, is this how does this differ or I don't know if it's a sort of an orthogonal notion to the idea of mutual interpretability?
Oh no, okay. It's actually, so of course if you have definitional equivalence, you in particular have mutual interpretability.
Okay, is this stronger then?
Yeah, it's much stronger. Yes.
Oh, okay.
It's a very kind of very strict kind of mutual interpretability. So because okay, so there is mutual interpretability. So you in a okay, so it's so what happening is if you have one say if you for example you could think about this on model theoretic level. So what it tells you, if you kind of have a model of okay, theories T and U are mutually interpretable, then if we have a model of T, then we could construct inside it a model of U, and vice versa. But it doesn't give you one-to-one correspondence between models of T and U. So what would happen?
Right.
You construct, for example, in theory T, you constructed some very particular models of U. I don't know. For example, you could, I don't know, say ZF plus continuum hypothesis and ZF plus negation of continuum hypothesis will be mutually interpretable, of course. But when you're constructing, for example, when you're constructing, so at least like natural way how you, okay, the simplest way how you could interpret continuum hypothesis in negation of continuum hypothesis would be to construct, to make your interpretation just constructible universe. But like, of course, this doesn't capture all possible models of continuum hypothesis, because of course there are non-constructible models of continuum hypothesis. Yeah, so, but okay, in kind of when you connection the definitional equivalence, you have one-to-one correspondence between models. So in particular, this means, of course, that you like this specific, very special kind of interpretation that you extract from definitional equivalence. So basically when you kind of range over all possible models of T, you get all possible models of U and vice versa.
So I mean, there's mutual interpretability, right, where each theory interprets into the other one. There's the stronger version, which is, I think, close to what you're talking about, which is bi-interpretability, where the two translations are inverse. But I mean, then there's this issue about whether or not the correspondence is an actual bijection, which I think so that's the strongest version. Are you requiring that? That you know, the entire domain should correspond? Because I think that's what's called synonymy.
Oh yeah, right.
Maybe also definitional
equivalence. Yes. So definitional equivalence also is known as synonymy. So okay, with regard to connection with bi-interpretability,
they're often equivalent, but maybe
yeah. So the bi-interpretability is actually, of course, it's kind of else. It tries to capture the same idea, right? So that
So which, I mean, are you asking for the strongest possible one? That this translation actually is a bijection between the domains? Do you care?
Yes. Yeah. So essentially, yeah. Right. So
okay.
Here, Yes, but okay, the point is like, in fact, for sequential series, so essentially all the kind of
Right, I mean, exactly. Reasonable theories. Sure, I've read the paper, but yeah, but a priori, yeah, okay, fine, thanks.
Yeah, no. Okay, so I should mention, yeah, so there is this theorem of Visser and Friedman that, okay, so for very large class of series, so namely for sequential series, by interpretability is equivalent to definitional equivalence. So
right, I mean, it's like some sort of like prototypical Schroeder-Bernstein argument at the heart of it, right? Yes. That, you know, I mean, it's a cute little thing, but yeah, okay. Right, so either of those, but definitely more than mutual interpretability, which is just sort of two random interpretations.
Yes, yeah. So essentially, the point here is like mutual interpretable series not necessarily kind of speak essentially about the same thing, right? So the kind of you could kind of collapse some information that is present in mutually interpretable series. For example, I think okay, I'll give another example. If you have, for example, you could have second order arithmetic, and you could have ZF minus, where ZF minus is ZF without power set. So these two theories are mutually interpretable, but in fact, so the range of possible models of ZF minus, in a sense, is larger. So in particular, so of course, starting from second order arithmetic, you could construct a model of ZF minus. But this always will be a model where all sets are countable, but not all models of ZF minus have all the sets being internally countable. So yeah, so in a sense, kind of like so in this example of mutual interpretability, you kind of collapsed this some information that was some range of possibilities that was present in ZF minus to like much kind of to a smaller range of possible models that are models.
All right, I'm just checking because I read this paper of Joel's. I think if I say it right here, so I mean, if you take, say, algebraically closed fields of characteristic 0 and real closed fields of characteristic 0, that's not. But if you add complex conjugation, I think, to the algebraically closed fields of characteristic 0, then maybe, or no. I'm trying to remember this. They don't get a bijection of domains, but anyway.
Yeah,
the point is that's not sequential, but I said, yeah, that's not sequential, but otherwise you do get almost inverse interpretations if you add the complex conjugation. Otherwise, you can't do it at all in one direction.
Okay, I'm not familiar.
Anyway, it's a nice. There's a nice posting of Joel. Sorry to interrupt, but I mean it's just I'm into this.
Yeah. Okay. Yeah. Okay. Okay. Anyways, so okay. So now we kind of figure out what this notion of definitional equivalence is. So now let me state the main theorem that I will be proving today. So that there is a theory that is definitionally equivalent to Peano arithmetic, and that has a non-standard computable model. That is a computable model such that the corresponding P model is not isomorphic to the standard one. And in fact, the theory will have infinitely many non-isomorphic computable models. So yeah, so of course, okay, regardless of how you define standard model, at most one of them could be standard. So in particular, there will be non-standard ones. But anyway, so this is of course doesn't matter because as I told you, basically there is, if you have two definitional equivalent theories, then there is a natural one-to-one correspondence between the models of the series, and hence basically when you're given this a model of this definition equivalent series, it has kind of canonically kind of could recover a model of Peano arithmetic, and hence it's very natural to talk about standardness there. Okay, so this is the theorem. So now, okay, so basically for the rest of the talk, I will be proving this theorem. Okay. Okay, so in fact, I will be proving something more general. So let me state what exactly I will be proving. Okay, so let's consider theory ZF plus minus inf. So this will be Zermelo-Fraenkel theory, where we removed axiom of infinity and added the axiom of transitive closure. Okay, so it's actually the fact that we need to add transitive closure. It's, I think it just it depends on how exactly you axiomatize Thermolo-Frankel set theory. So basically, if you axiomatize it by the axiom of regularity rather than the schemata of induction of membership induction on sets, then you need to add axiom of transitive closure. And if you instead of axiom of regularity, you add the schemata of induction on sets, then you don't need transitive closure, so it will be provable. Okay, anyway, so this just some technicalities. Yeah, else. Yeah, okay. So the theory, and so the what's important about this theory is that it's on one, so it has two natural extensions. Namely, we could either add axiom of infinity to it, or we could add negation of the axiom of infinity. Of course, if we add axiom of infinity, then we simply get Zermelo-Frankel set theory. And if we add negation of the axiom of infinity, then we get the theory that I denote here ZF plus phi. That is a theory definition equivalent to Peano arithmetic. So it's essentially very natural theory talking about hereditarily finite sets. Yeah, and then there is, actually it was proved by K and Wong that they are definition equivalent. Yeah. So again, the definition is very simple in this. Okay. Conceptually, it's very simple, but like I guess to actually construct it, it's a bit of work. So one direction is easy. So namely, if you want to interpret, so if you define membership from addition and multiplication, then you simply do Ackermann membership. So Ackermann membership is this, right? So yeah, so basically we're writing number y in binary, and then you're looking at an x bit of y is y. Right, so you're writing this in binary, and then you're looking at an x's bit. And so if it's 1, then x is an element of y, and if it's not 1, then x is not an element of y. And this basically allows us to import hereditarily finite sets by natural numbers. And then to make this okay, so this way we're showing that ZF plus phi is a kind of subtheory definition extension of Peano arithmetic. And to go back, we need to recover plus and times or on sets. Where so basically now think about that our sets should correspond to natural numbers, because we all fix this coding, right? So we can offset by natural numbers, and then we need to go back. So we need just reasoning in terms of sets. We need to define what is what set corresponds to sum of two sets when we identify sets with natural numbers coding them. Anyway, so there's a bit of technicality how we go back, but if you could do it, it's now of course not a problem at all. Yeah. Anyway, so this is basically how this definition of equivalence works. Okay, and so for technical reasons, it actually will be easier to work with theories in that are more closely based on ZF plus fin rather than Peano arithmetic, and also it will allow me to prove a more general result. So this corollary below. Okay, anyway, so the theorem that I will be proving today is the following. So there is a theory T0 definitionally equivalent to ZF plus minus inf, such that any numerable extension of T0 has a computable model. Okay, and of course, okay, first of all, of course, it implies the theorem from the last slide. So the theorem, so since PA and ZF plus fin are definition equivalents, in particular, it means that T0 plus negation of infinity is definition equivalent to Peano arithmetic, right? So this will be T0 plus negation of infinity. And okay, so now it states that we have a non-standard computable model. Okay, for example, you then add to T0 plus negation of infinity some fact that is false in the standard model, whichever is your favorite fact, right? So yeah, for example, you could add, I don't know, negation of consistency of Peano arithmetic or whatever. I mean, something that is false but still consistent with Peano arithmetic. So
I just want to check I mean, because I read the discussion you just had about the Ackermann coding and all. That was just a review of the K. Wong paper, right? That's not the T0 you're doing, right?
Oh no.
It's the nice illustration. That's actually why I'm here, because I read that paper 15 years ago and it got me into this subject. So anyhow.
Okay, yeah, okay, that's good, yeah. Okay, anyway, so this, so what I'm saying that we have this, our theory here will be this T0 plus negation of infinity, and in order to obtain a non-standard computable model, we consider theory T0 plus negation of infinity plus some phi, where so phi is also such that this. So this thing is consistent. But phi is false in the standard model. Okay. Yeah, so basically this is what yeah, so we're doing this, and then by this theorem here, right? So this main technical theorem, there will be a model of that theory, so with this additional false sentence. And yeah, since we had that false sentence, this can this forces the model to be non-standard. Okay, so this is basically how we prove this result about theory definitional equivalent to Peano arithmetic with non-standard computable models. Okay, okay, so this of course this theorem also of course has other nice corollary now about Zermelo-Fraenkel theory, since of course the theory ZF plus minus inf is also has this also has Zermelo-Fraenkel theory extension. So namely we have just the theory T0 plus inf that is definitionally equivalent to Zermelo-Fraenkel theory, and it has a computable model, so by the theorem above, right? So yeah. So we have kind of computable models of Zermelo-Fraenkel theory. Okay.
Fedor, can I ask you a question? Sorry, just for clarification.
Yeah.
Could you go back to the previous page for a second? In your main theorem, when you say, I have two questions. One is when you say the corresponding PA model, just to be clear, the corresponding PA model is the correspondence that the definitional equivalence is giving you, right? It's basically, you have a model of this theory, and then any model of PA, basically there's a one-to-one map between models of PA and models of your theory. And when you say corresponding PA model, you mean in this grand scheme where models of this theory are put into one-to-one budget correspondence.
Yes. Yeah, right. So there's a very canonical way how it could go back and forth between PA model and most of the theory, because I think you, since PA doesn't have non-trivial by interpretation, in a sense, you don't even need to fix definitional equivalence here. But but if you have big definitional equivalence, then it's very so kind of this joint definitional extension. Then it's very simple to go back and forth, right? So you could, from any model of PA, you could go to this model of this joint signature, unique way, because it's simply definitional extension, right? So all predicates in the joint signature have just explicit definitions in the language of PA. And then you could then forget about signature of PA. And this way you obtain a model of the theory T0 plus negation of infinity, and vice versa, right? So because now you have explicit definition of additional multiplication in T0 plus infinity, then hence you go to this model of joint signature in a unique way, and then you could forget about additional about the signature of the theory T0 and obtain a model of PA.
Okay. And my other question is very quick, just to be clear that whether the standard model, if we just take the standard model and look at the corresponding model of your theory, would that corresponding model also be computable?
Yes, it will. It will be, okay. because in fact this this more precise language of T0 will have one ternary predicate symbol, and basically in standard models it's just simply a computable predicate.
Okay, very good, very good. Thank you.
I mean, just in that example annotation at the bottom, when you say, so what you're going to do is you're going to first give it T0 with this property, and then an explicit statement phi in that signature, and it's such that the translation into arithmetic is false in the standard model.
Yeah. Okay. No.
Okay.
Actually,
so it's not just an issue of isomorphism. It's actually an issue of the elementary theory. Maybe they're equivalent here because of countability. I don't know.
Yeah. So the point is you could go back and forth between languages, right? So if you have a sentence in the language of T0, then you could. Then you could translate it to the language of arithmetic, because all predicates in the language of T0 has arithmetical definitions. So and vice versa. So
and I guess if you require the correspondence to be a bijection between domains and everything's countable, and then elementary equivalence and isomorphism will be the same. So yeah, okay. So it's just about the translation.
Yeah.
Okay.
Yeah. So in essence, what I'm saying, that definitionally equivalent theories essentially are the same theories. So they kind of just choosing different kind of basic predicates, basic elements of signature. So what is in essence it's the same theory.
Okay, actually over there. So when you say T0 plus not infinity, is T0 in the signature of set theory?
No, it's okay. It's
so how do you phrase the axiom of infinity then?
Okay,
I was going to ask the same thing.
Yeah, I was going to ask before, but then I realized that since you have replacement, I mean, everything I would have asked about was irrelevant, but now I'm really curious.
Oh, okay, yeah, sorry, yeah. Okay, so basically the point is you could define, I could, let's be simply explicit. So, so basically T0 will have this, the only predicate symbol to be an only ternary predicate symbol S, X, Y, Z, and then you could define membership from it as follows. So X is an element of Y if and only if for all Z, S, X, Y, Z. Right, so this is basically how you define membership from this predicate S that will be in the signature of T0, and then using the definition of membership, you could express negation of the axiom of infinity. You simply write down usual axiom of negation of the axiom of infinity, and replace all occurrences of membership with this definition of membership, and that's all.
Oh, I see. And then whatever axioms you have about S, you'll prove that Oh, I see. The point is, this is the actual definition, and then you're going to verify that this satisfies ZF minus plus whatever.
Yes. Okay. Yeah. So the point is, okay. I think maybe it's simply a bit. Young simply not very used to this terminology. But what I'm doing here is, in a sense, it's a very standard thing to do, because when we are
Power of ternary relation.
working with theories in logic, so we are very casually using definitional extensions. So we casually define some additional predicates and functional symbols and starting to use them as if they were in our signature, right? So this is extremely casual thing to do. Yeah, and so here I simply kind of course, I kind of exploiting this, so I kind of having this situation where I kind of have this. So, okay, basically in the situation of definitional equivalence, so what's happening is kind of you have several possibilities what could be your basic predicate symbols.
But somehow, I mean, I don't know the details how to do this, but somehow it wouldn't work if you had an existential quantifier in front, or
okay, no, it would like, I mean, okay.
I mean, how general is this trick?
Okay, no, I mean, it doesn't like, okay, so, okay, for this particular S that I have here, of course, like the definition is the one that I written, but I mean, if you you could switch from S to its negation, and then you, okay, no negation, okay, anyway, so you could very easily, by the same method, constructed other S, such as.
Oh, of course, okay, yeah.
Basically,
yeah, no, that was, yeah, no, that's clear. Yeah, that was not a good question. Okay, yeah, thanks.
Okay, yeah, and so so basically in a sense, of course, when kind of working with the definitional equivalence series, you kind of casually use sentences written in like in the language of kind of with this joint definitional extension, and this is not a problem at all. Anyway, so okay, yeah, so it's simply a bit confusing, but then nothing actually complicated happening at this point. Okay, so this is basically the main theorem. Okay, so what I think I should mention, since I started to discuss this Tennenbaum theorem for thermal variable theory, there is this, in fact, actually the analog of Tennenbaum theorem holds also for the theory ZF plus phi. This is the result of Ali Annette, Albert Visser, and James Schmerl. Yeah, so that so the result is that the only computable model of ZF plus phi is the standard model. Okay. So in particular, of course, we couldn't have chosen T0 to be simply ZF plus minus int, so this wouldn't work. We need some difference. Okay, so. In fact, I think so. Basically, if you kind of think about what kind of signature might have worked, it's quite clear that like this that this alternative signature should have some a bit weird properties, because like if you kind of just start using some standard predicates, it's kind of just looking at the techniques used to use normal Tennenbaum theorem and this theorem of Anayat with Schmerl, so it's kind of clear that like the techniques generalize for a lot of signatures. So and yeah, so one need to be quite basically this signature for which it fails, like it's highly non-arbitrary signature. So one need to be quite careful defining it. Anyway, so now let me go to actually define this ternary predicate S. Okay, so what exactly will be doing? So okay, so I already told you the only symbol in the signature of T0 will be a ternary predicate symbol SXYZ. Okay, and so the way how I will define T0 will not actually even be explicit. So what I will be doing is the following: I will work inside the series ZF plus minus int and define certain ternary relation as XYZ. And this ternary relation will have this property that I already written, so that that you could recover membership from it, right? So if you kind of by kind of doing this universal quantification of the certain variable, you recover membership predicate. And so, and as soon as we have done this, then of course we obtain a theory definition equivalent to ZF plus minus nth. Because more precisely, we're doing the following. So we define this ternary relation, and then we could simply look at the set of all sentences in the language with just ternary relations that are provable in ZF plus minus nth, and this is our theory T0, right? So T0 is just a set of phi that is in the language of S, such that ZF plus minus inf prove phi, right? And yeah, and so basically, and then this is a definition equivalent to ZF plus minus inf, because in one direction you could go by this definition of membership, and another direction it's basically we're just taking the definition of S inside ZF plus minus inf. Okay, so this is basically how the construction is done in general terms. So now, okay, but of course not any S like this would work. So we need some a bit more properties from our S. So next I will construct like S with some more particular properties that will be suitable for proving the theorem about computable models. Okay, so this kind of the key notion here will be this notion of okay, so first consider the notion of good finite S in structure. So okay, so we can start, okay, we are working inside this ZF minus nth, and we consider the finite structures in the signature with one ternary predicate S and one binary predicate in. Okay, and so here, right now I don't kind of require this structures to be absolute, right? So you could interpret membership in some way and S in some other way, and not necessarily the same as in our ground model. Okay, and so basically I kind of, in fact, I'm interested in finite structures like this, and the only property that I demand here is this one. So this is basically it's saying that in a sense the structures are behaving like finite fragments of our big predicate S that we eventually want to construct. So basically we want that if A is an element of B, then for all Z, S of A be Z. Right, so this is basically what we want from fragments of our big kind of S defined on the whole universe, because yeah, so if you want to have a kind of equivalence eventually equivalence, so even for finite fragments we should have this side of the equivalence, right? So kind of if some yeah, okay. Yeah, and so further, if I'm talking about structures, by default, I will mean this good finite S in structures. Okay, so next, I have this notion of neutral extension, and this is the following idea. So we say that the structure B neutrally extends structure A if it has exactly one additional element in the domain, so this element V, right? So yeah, and what I demand is that this additional element V, it kind of membership independent from the rest of the structure. So basically, it's not an element of any element, and doesn't contain as its member any other element of the whole structure. So okay, so I guess technically one could call this V and your element, but probably it's not the best way to think about it, because the way how we think, I'm thinking about the structures A and B are like that. They're kind of they're not the whole universe, but they're fragments of the universe. So it's more like this additional element V is kind of just kind of like this element to the side of what have been happening so far, right? So it's kind of just you kind of just choose some set that is just somehow not connected to anything that we had before. Okay, so this is basically what neutral extension is. And okay, so key property that I want from the predicate S is the following. So if so that for any absolute structure A, absolute here means the following. So we're assuming that we already defined this predicate S, and when we would define this predicate S, then we will have this notion of absolute structure, and absolute structure simply means that it's kind of finite fragment of the whole universe, right? So it's kind of so it's just it has this finite sense. It's kind of and then in the interpretation of membership and S are the same as in the universe. Okay, so we're saying that for any absolute structure A and its neutral extension B, and this extension is not necessarily absolute, and we say that any neutral extension could be collapsed to an absolute neutral extension, right? So this basically means that we have some neutral extension by some element V, and we could replace this V with some set V prime, such that the resulting structure B prime will be absolute. So this is the.
I'm sorry, I followed everything, but the definition of absolute structure, could you write it somewhere?
Oh yeah,
I just did not get it. Or,
Okay,
I
mean, yeah. Sorry, yeah. Mm-hmm.
Okay. Oh, I see. We're only dealing with finite structures at this point.
Yeah.
Oh, I see. So it's not just that you're denying infinity at this point, but you actually, the structure itself at this point is finite.
Yes, yeah. In fact, okay, you'll see in a sense like what we will need in a sense external finite means not internal finiteness, or like it's internal finiteness in the approximation.
Yeah, but you can say external finiteness because
yes,
I
can
just enumerate the elements with variables, right? That's what you mean. Okay.
So A models A element of B if and only if A is an element of B, and A models S ABC if and only if S ABC. Right. So here I already assuming that we already define this ternary relation S. Right. So okay, so absoluteness is actually it's just absoluteness. So nothing really going on here.
Actually, now I'm more confused. Is this basically your way of saying it's standard? I mean, you're using epsilon. You have that by implication, which I'm assuming is happening in the meta theory, right? And you're saying that A thinks little a is an element of B if and only if A actually is an element of B. Is that what you're saying?
Yes, but I'm working inside ZF plus minus inf, right? Right. So kind of it's working internally. And what I'm saying is that being absolute simply means that it's finite fragment of the universe, right? So
so when you write that, when you're writing down an A models that sentence, you're actually evaluating, you're actually thinking of evaluating that internally, even though is that, I mean, I'm just trying to gauge what's similar and what's different about the two sides, because it's the same thing I try to teach my students.
No. So, okay, so
and I'm lost.
Okay, so when we're working in ZF plus minus n, so all our objects are set, right? So we
yeah, of course.
Something is an element of something else.
Sure.
So, but at the same time, we could formalize the notion of finite structure, right? So, what we kind of here, we're kind of talking about finite structure. And then we're saying that if so structure is absolute, if it's correct about membership and it's correct about
okay, right. Okay, so here, let me try to paraphrase, because this is great. This is like the grown-up version of it. Okay, you're formalizing your model. You're formalizing the meta theory. You're doing your model theory internally in your Z and your whatever ZF minus plus whatever. And then absoluteness basically means standard as understood internally within that, because you could talk, because now that you're formalized, you could internally talk about what's standard versus non-standard internal to that. And that's what you mean here.
Okay.
Cool. Thank you so much.
I think people in set theory, they use similar terminology. I think it's about when
But in set theory, I think, I mean, at least what I'm used to, I mean, I'm not really a set theorist either, but they'll talk about absoluteness when they're talking about extensions, for example, extensions of transitive models, and saying that the membership predicate has the same meaning. So that's basically what you're doing here, but there's this extra internalization aspect of it, I think, but yeah, otherwise, yeah, got it. I got it. It's brilliant.
Anyway, yeah, so it's I think it's all very simple. Anyway, so yeah, so this is kind of abstractness. Yeah, and so yeah, so the point is like if you kind of this is of course this is certain kind of universal property, right? So we're kind of saying that essentially what we're saying that if you kind of that any possible neutral extension is realized inside, right? So that if you kind of think about some kind of basically, okay, basically if you have some finite fragment of your universe, and you could kind of add some element to it. So basically, whenever you add one element to it with any possible interpretation of S, then this additional elements is realized some way in our universe. Also, this element should be kind of membership independent from everything that we had before. This is basically what this talks about. Okay, so we will need a predicate S with this property. And in fact, so this will only things that will matter. So the particular definition of S will not matter for the proof of the existence of computable models. So we just need this universal property. Okay, so I think what I should already mention, then of course this universal property already guarantees that we could fully recover membership from it, because so okay, so we kind of if you kind of have this universal property, then we recover other side of the implication, and the reason is that so basically if I assume that so for example A was not element of B. So if A is not element of B, then you consider of course this two element structure on AB, right? So and the point is now you could find C that would witness negation of SABC. So then there exists C such that SABC, and so you could find this by this collapsing, right? So you just okay. So first you kind of okay. So let's focus C prime. So you first find just consider some non-absolute structure with some element C, where you have this negation of SABC, and then you collapsing C to C prime to obtain this absolute version. Right? And hence, yeah. So hence you're getting like in the whole structure, you will getting this equivalence between membership and universal closure of S. Okay. Okay, so now we need to construct this predicate S. Okay, so okay, actually, it's there's nothing interesting about this. But basically, what I'm doing, I'm defining this by transfinite recursion on levels of von Neumann hierarchy. Namely, so on step alpha, I define the restriction of S to V6 alpha. And then kind of the point is like when you jump in 6 levels in commutative hierarchy in one step, you have a lot of additional sets, and then you have all possible configurations realized there. They have a lot of space, and basically you kind of have enough space to extend this S so that we will guarantee this universal properties that we want. Okay, more precisely, what happened is the following. So basically, given some pair A structure AB from the 6 alpha level of von Neumann hierarchy, such that B is a neutral extension of A by some element V, and A is absolute. So basically, the citation we are interested in. we basically fixing some element v prime that basically witnesses this collapse of b to the structure b prime that will be absolute. And this v prime should be, of course, from this new part. So this it should be element of whose rank is below 6 alpha plus 6, but above 6 alpha. And and then, of course, this v prime should be distinct for all pairs like this. And then when we fix this v prime, so what we could do is we simply kind of interpret as a minimal possible way to kind of do what we want. So basically, we kind of we have this all this structures b primes, and so we want s to be interpreted. So b primes are kind of their domains are like subsets of v6 alpha plus 6, and so we're simply interpreting s on these restrictions as interpreting the structures b prime. And everything outside is we simply put not s of x, y, z, right? So it actually doesn't matter how we. Actually. Okay. Sorry. Actually, I think what I'm thinking is wrong. So actually, it should be not the least, but should be greatest. I'm sorry. So basically due to the way how we set up s, when we kind of adding for some triple s x y z, it kind of it doesn't matter. It kind of doesn't break our property, and if we kind of arbitrarily adding negations, it's not particularly good. Anyway, so it should be greatest. But anyway, the point is like what matters is like we have this particular finite structures where it does matter how we define s, and outside we simply always say that s is true. Okay, so the only thing that we need is kind of to interpret this v primes, and so basically okay, we could do it in an explicit way like this. So v prime will be 6 alpha a Kuratowski pair consisting of ordinal 6 alpha plus 3 and pair ab. Anyway, it doesn't really matter. So the point is like this particular element is its membership independent from everything from level 6 alpha for Neumann hierarchy, and it's inside this level. So inside this v6 alpha plus 6, and not inside v6 alpha. Yeah.
So just to get, I mean, the plus 3. You need that because of something about the amount of nesting in the Kuratowski pair, and then the 3 determines the 6 to give you enough space for all of them, something like that.
Yeah, actually, I don't exactly remember.
I mean, if you used Wiener pairs or something with 3 levels of set braces, would that force those numbers to be different?
I don't. Again, I don't remember. But
okay, it's just that's like a computer programming question.
Yeah. No. Actually, there's basically somehow.
Because I could give half of this to my students to read, right? So.
No, actually, but basically you just need to fix somehow this element.
I'll read the paper. It's in the paper, surely.
Yeah, no, but it's actually the verification is not hard, right? So, but but actually, I don't remember why exactly I have done exactly this construction. It's basically an engineering problem, right? So
sure.
You need to kind of fit this element there, and you need to guarantee.
But there's like a margin of 3 or 4 that comes up all over the place when you use Kuratowski pairs. Right, and then people will talk about Klein pairs, but then that's not good in the finite case, etc. But anyway,
I mean, I'm pretty much sure that it could be much more optimal than what I'm doing.
Yeah.
If you kind of
I'll crunch the numbers myself. This is a lot of fun.
Yeah, but I just didn't care about this when I was doing this, and of course it doesn't matter for what I'm doing. But yeah, of course I'm pretty much sure that one could be much more optimal here. Okay, anyway.
And why do you want the greatest? Why is that important rather than the least? Is that
so because we want this implication, right? And basically, if it would be the least one, this implication might break. And if it's the greatest, it will not break. So basically,
I mean, but that's because of some detail in the argument. Why? I mean, there's an actual reason why greatest works and least doesn't, based on your maximization or something?
What I'm saying. So okay, in the end we want in the end we want so basically we want that our structure has so satisfies this property, right? So for any element feature, we want our universe to satisfy the property. So for any A, B, if A is an element of B, then for any Z, S, A, B, Z, right? And basically, if you kind of put S to be least, it will break, right? So if you arbitrarily adding kind of this point triples where you have negation of S, then this will break this implication. And if you kind of know, if you're careful about this and you're adding this kind of adding negation only in kind of carefully chosen places, then it's fine. So hence, basically, the natural way to do it by choosing the greatest one. Right? So not to break this implication. Okay. But yeah, it's just some technicalities as a thing. Okay, I think that like this whole explicit construction, it doesn't really matter for the rest of the argument. So it's kind of as soon as we have this universal property, it's all good. Okay. Okay, so now let's actually go to the proof of the main theorem. Okay, to remind you, we want to prove the following. So we want to construct. We already construct the theory T0. We show the definition equivalent to ZF plus minus inf. Okay, so now what we want to show is that any enumerable extension T of T0 has a computable model, or more precisely, of course, consistent enumerable extension. Okay. Okay, so so this is kind of standard thing in computability theory. Okay, so first the point is you have extension, enumerable extension of T0, then there is a delta to completion of this extension, and furthermore we could kind of make this completion to be in the language with Hankin constants. So it's kind of having this Hankin constant C phi x with the usual property, right? So if phi of x, then phi of C phi x. Okay, and so as soon as we have this delta to completion, then as usual in computability theory, basically any delta to set is a limit of phi of computable finite sequence of sets. Okay, so this basically means that phi is an element. So phi is kind of a theorem of U if and only if for all large enough and small, phi is an element of U and small, and phi is not a theorem of U if and only if for large enough and small, phi is not element of U and small. Okay, so for people that are not are not that comfortable with this with these things, that let me give actually explicit construction for the delta to completion and its and this computable sequence of finite sets that such that the limit is our U. Okay, so we could construct U and UN as follows. Okay, as usual, basically fixing this enumeration of all sentences with in the language with Hankin constants, and then we define the series in a series of finite sets U and M as follows. So UN0 is empty set, and when we define U and M plus 1, we consider two. This is actually type. This should be anyway. Yeah. So when defining UN plus M, so U and M, we basically UN M plus 1, we consider two possibilities. Namely, we are looking at theory T plus U and M plus phi. Okay. Yeah. Sorry. It should be phi M. Not phi M. Plus phi m, so you can see the you can see the next kind of this next sentence in our enumeration, and basically basically interested in whether this theory is consistent or not. But since we want this to be computable, we couldn't actually ask whether it's consistent or not. but we could ask whether like this consistency is witnessed by a small number. So what basically witnessed by small number means, okay, so for simplicity, if you think about that, axiomatization of T is not just enumerable, but actually decidable. Then you basically asking here whether there is a proof of contradiction of the length less than n. If if for T you don't have a recursive axiomatization, that you need to be a bit more careful what exactly it means. So basically you want to have this kind of some finite witness for consistency. But yeah, but basically if T has a decidable axiomatization, that you simply could ask about the kind of that there are no proofs of contradiction of the length less than n, and length here means like length as a binary string, right? So we can want to have just finitely many possibilities to make this efficiently checkable. Okay. Anyway, so kind of have approximation to consistency, and then you kind of defining UNMs according to n's approximation to consistency. And then your sequence UN will be this diagonal UNN. Yeah. And then you could check that actually the sequence UNN has a limit, and this limit is a consistent completion of the theory T in the language with Hankin constants. Okay, so this is basically how this explicit construction works.
Wait, so what is the delta 2,0? I think I had the wrong interpretation before. It's not that it's an actual completion which is described by a delta 2 predicate, or is it something which is complete for delta 2 sentences?
No.
I was thinking it was the second one, but it's the first one, right?
Yeah. It's simply as a kind of as a set of sentences. It is a delta 2 set.
Right. I mean, this is basically like the arithmetized completeness theorem that you're doing here.
Yeah.
Okay, fine.
Essentially.
Fine. I mean, I was reading that like last month, so all right.
It essentially is exactly arithmetized completeness theorem.
That's why it's delta 0. Because that's what you get when you do it. Okay.
Yes. No. I'm simply basically for convenience, I kind of gave this explicit definition here, because so I mean yeah, so I think of course like computability theories, then nothing new happening here, right? Kind of the idea that we have delta 2 set, that is a delta 2 set is the limit of computable sequences, a very standard thing. Yeah, but anyway, okay. So but actually this sequence that we have constructed wouldn't be kind of completely suitable to what I will do next. And what kind of I want to modify the sequence UN to kind of to have information about this universal property of our predicate S that we have. Okay, so first of all, let me restate this universal prop. Okay. This universal property in more kind of in this more syntactical way. In the more syntactical way, I restated as follows. So we can see I consider some structure or A on Hankin constants. So here structure, to remind you, means finite S in structure, and on Hankin simply means that elements of this structure are Hankin constants. So this Hankin constant from the language of theory U. Okay, and then we consider some its neutral extension. So we're getting some additional elements that actually might not be Hankin constant, or we don't care if it's a Hankin constant. Okay, and then so basically we always have the following property. So the theory U proves that if diagram of A holds, then there exists X such that the diagram of B with V replaced with X holds. Okay, well, of course, by diagram I simply means atomic diagram. Okay, so yeah, so this in fact is just kind of very easy corollary of our universal properties that we had before. So our universal properties that we had before told us the following. So if you kind of internally, if you have a finite structure and you have some element, then you could kind of collapse this element to make this absolute. So you have this absolute structure, and you add some elements that is not necessary, kind of not necessarily absolute, but they kind of have some relations with these previous elements. Then you kind of always could collapse this additional element to obtain an absolute structure. And what I'm stating here is essentially the same thing, but okay, so before it was stated for kind of this internally finite things, but now I kind of stating this for externally finite things. So I kind of, and more precisely, structures that I consider right now are just structures whose domain consists of Henkin constants, right? So kind of A is this, okay, kind of very, kind of inside U, basically some structure A and Henkin constants. Then inside U, basically there are two possibilities. Either it's kind of actually so A actually is correct, agrees with you, or A does not agree with you, because of course you have all this information about kind of connection between the Henkin constants that are elements of A. And yeah, and so here basically stating that kind of A is kind of gives the same description of connection between this Henkin constant as U. Okay, so we kind of, this is the premise. So we're assuming that A is correct, and we're concluding that there kind of exists extension of. And so basically, if we have the sum neutral extension of A, then we kind of put we have this additional element such that the kind of replacement of additional element of B with this X gives a kind of a correct structure. Okay. But furthermore, of course, instead of having this with existential quantifier, we could do it with appropriate Henkin constant, right? So because, of course, it's simply existential sentence, and simply it corresponds to certain Henkin constant, and we simply put we could I denote this canonically chosen Henkin constant as E of AB, and hence I simply have this quantifier-free sentence, right? So if diagram of A, then diagram of B with V replaced by this canonically chosen Henkin constant E of AB. Okay. Yeah. So this is regardless of what A and B are, this is the theorem of U. But of course, like if A is not correct, then like the premise of the implication is simply disprovable in U. Okay. Anyway. And now, basically, what I'm doing, I'm looking at the so sets UN. And I am closing them under this rule corresponding to this implication. And the rule is the following. So basically, this is UN primes are the least sets of sentences such that whenever diagram of A is a subset of UN, then the diagram of B is, okay, basically doing the same thing as above, right? So having this structure B prime with B replaced with this E of AB. So okay, basically, if diagram of A was subset U of that should be UN prime. Was subset of UN prime, that the diagram of this kind of canonical collapse of extension of A is also subset of UN prime. Okay, then one of it's not entirely trivial. One need to, but one could show the following: so that this sequence UN prime is in fact a sequence of uniformly computable sets. They, of course, they actually, in fact, will not be finite in general, but they always be decidable sets. And the limit of UN primes is the same U as before. So, of course, this is kind of follows from the fact that kind of U, of course, is closed under the same rules. But yeah, but so here what you need to check that kind of when you're doing this closure, then yeah, so basically this kind of this closure will be decidable, and this when we're doing this closure, this kind of doesn't break up this limit behavior. Okay, I will not do this, but yeah, but one could do it. It's not that hard. basically you kind of need to use a fact that it's very specific rule, and it's yeah, it's kind of easy to do this closure. Okay. Oh. So now let me do the construction of computable model. Okay, so we have already done this all the preparatory steps, and now we could actually start the main construction. Okay, the construction will be basically the following. So I'll construct this finite, the sequence of finite S structures. So or that whose domains are just initial segments of natural numbers. And S structure means that kind of now we don't care about membership, and we're simply taking our S predicate. And at the same time, I will have the sequence of finite S in structures on Hankin constants, D0, D1, D2, and so on. And this these I's will be kind of embeddable into MIs, right? So MI, so the point is like have the sequence MI, and like DI is like this interpretation of Hankin constants of some of the elements of MI. And we have this, when we have this interpretation of Hankin constants, we also have interpretation of membership. Okay, and our final model will be this, of course, union of MIs. Okay, so in roughly the construction will look like this. Okay, so now let me describe the properties of these sequences that we will eventually guarantee. Okay, so we have these three sequences, and so basically it looks like this, right? So it kind of the sequence of MIs, so M0, M1, M2, so on. Right, so then actually DIs are simply embeddable here, right? So D0, D1, D2, so on. And the point is that in fact this embeddings that do not necessarily agree with each other, right? So the sequence DI is not necessarily a sequence of expanding structures. So we kind of could do this revisiting of what we're exactly doing with DIs. However, what we demand is if you have some natural number K, and actually the structures MI, they will be kind of eventually they're getting larger and larger. So at some point, every number K becomes a member of this MIs. So and for any natural number K, this value Gi, so this inverse Gi minus 2 minus 1 of K, so it should eventually stabilize to be some Hankin constant. So what I mean by this, so from certain point, this K is always in the range of Gi, and furthermore, after some point, this kind of the pre-images of K are the same, right? So this eventually, despite like it's kind of we could have a revision. What are kind of the Hankin constants associated with K, eventually this should stabilize, and we denote the stabilized value as T of K, so some Hankin constant. And what they want with this limit behavior is so that basically M is correct about predicate S, right? So that we have M of S of K1, K2, K3, if and only if you proved that S of T of K1, T of K2, and T of K3. Okay, and finally, of course, like what we also want is that any Hankin constant from U, in fact, is probably equal to some T of K. And basically, if you kind of have all these properties, then this guarantees that this limit of DIs. Okay. Yeah, okay, so actually, if you want to guarantee that the limit of di is model of u, we need a bit more. We need actually to know that the limit of di is correct about membership, not just about S. But anyway, we will have this also. And yeah, and of course, what I written actually guarantees that M will be a model of the restriction of U to the original language. Okay. So this in rough words, this is what the construction will be. So now I have a question: how much time do I still have? Yeah.
You can go for about 10 more minutes, I think.
For how long?
About 10 more minutes.
Oh, okay. So now, okay. So I think actually at this point my slides end. So, but I could sketch now. Let me sketch what exactly the main construction is. Okay. So what I need is to construct, of course, this MIs, so DIs and GIs. And on each step, the situation, okay, this will look approximately like this. So we'll we'll have what I want to call an onion model. So this, in fact, MI is structured like this. So you have this big structure MI, right? MI, and then some part of it, not all, is corresponding to DI, right? So this kind of DI. Okay, so this kind of DI is embedded into this fragment of MI. Okay, but then this, we don't have much kind of structure on this element that are outside of this image, but actually interesting thing happening inside this image. So actually, this image it's split into layers. So in fact, there are like these layers. Okay. And a lot of layers, and there's some structure on there. So basically, there's kind of each layer is kind of one fixed initial point. Okay, so in kind of in the here, in the beginning also. Yeah, there's kind of fixed point. Okay, so it's denote somehow like this initial point A0, A1, and so on. Some AK, or more specific, AKI. Okay, and so this the point is that this kind of additional this AIs they should correspond to just essentially kind of arbitrary Hansen constants. However, those additional points in this layers they couldn't be arbitrary constants. So they are of very particular kind. So they are always constructed as this constants A, So this basically this so this kind of consider as one of this layers. So layer some AJ, and then we have some additional elements. And so all these additional elements they of the form AAB, and in fact there's certain linear order. So this basically, so we kind of constructing them in very canonical way. So we kind of have this the rest, right? And then we have basically we kind of each next element here is obtained as this kind of canonical collapse of some structure, right? So kind of we have all three elements constructed before, and we are obtaining each next element as this canonical collapse of some S structure. Right? So the way how these layers are obtained. And so basically, due to the way how this kind of additional elements are constructed, what is happening is that if the theory UI, so if UI is correct, about something like this thing. So this, and then you have this AI. Then it's correct about this whole layer, right? So if you have this AI, and then we kind of adding this whole layer associated with AI. Okay, so this is roughly what's going on here, right? So this is kind of guaranteed with this closure property that we have here. And by correctness, I mean exactly this kind of condition. So this diagram of the structure is a subset of the corresponding approximation UI. So it's not UI, it should be UI prime, of course. Yeah. So correctness simply means that kind of atomic diagram is subset of UI. Correct. Okay, and basically during the construction, what the invariance that we preserving, that basically UI should be correct about everything, right? So UI should be correct about this whole thing, right? So so UI is correct about DI. Okay. Okay, so this is we preserve this on each step, and the way how we preserve it is the following. So basically, if we at some step we see that okay, the previous, so this kind of structure that we inherited from the previous step is not correct, then we are shredding some layers, right? So we have these layers, and basically we're looking kind of how many layers we should shred to preserve correctness, right? So kind of we shred this incorrect layers, and then we left out with just correct layers. Okay, so this is basically what we're doing. If we see some incorrectness, furthermore, basically this I not only want UI to be correct, I also the DI to be correct. I also want these choices of AJs to be in some sense minimal. So I have some order on Henkin constants, and basically I want this each next AJ to be least possible. Right? So because you can switch from some AJ to some Henkin constant with smaller index, then I should do so. So yeah, this basically means that kind of if we have non-minimal, despite the structure is correct, but it's in a sense non-minimal, then I also shredding this non-minimal kind of layers corresponding to this non-minimality, and yeah, and I left with the rest. Okay. Okay, so basically kind of the shredding thing, and then okay, so of course we not only need to do shredding, we also need to do expansions. And so the way how expansions are done is the following. So basically, if kind of suppose we have something like this. So we have suppose we don't need to shred anything. So we see that the kind of structure from the previous step is still correct. And so what we might see is that in fact we could add additional element here, right? So we could find this AK plus 1, K plus 1, such that basically if you consider like this DI and you add to it AK plus 1, so this AK plus 1 is some Henkin constant. So this so we kind of have this Henkin constant C. So if we add it to this DI, then we still we're getting something that is consistent with U prime I plus 1. So kind of this kind of structure consistent with the next step. And so if we see this, and then we choose C in some in minimal possible way, so we can connect this minimality conditions that I mentioned. Okay, so and we kind of could do this, and we kind of adding this C as additional element to mi. So the kind of in this case, mi grows by one element, and then what we could do is we kind of there have been all these elements that were outside of the integer di, so it's kind of those shredded elements of previous stages, and then we kind of could assign them to this newly forming layer in this canonical way, right? So we kind of doing this when we're having this, we added this additional element c, and then all these previously shredded elements could be assigned to the same layer by this construction, by this means of this kind of canonical collapses. And we could do it while preserving the structure of M, because M was simply S structure, and we could do this canonical collapses kind of for any S structure. Okay, yeah. Okay, so basically what's happening, so we kind of we are doing this by steps. In each step we are either shredding some layers, and then like this di becomes smaller, or we kind of adding one additional element to mi, and then di becoming the kind of the whole di plus one becoming the whole mi plus one. Sorry, I just giving, I think, rough impression of what's happening. Of course, I don't think it would be that easy to follow what I'm saying. Anyway, yeah, so basically this is the construction, right? So, and then if we do it what I have just described, then in fact one could show that we will guarantee this limit behavior. Yeah, so this, so basically some verification of this. So what actually needs to be shown is that basically you're showing that eventually first layer will stabilize. So we kind of at some point when we choose some A0 that will no longer be shredded at any point. So at some point A0 will stabilize, and this kind of layer will always be preserved and never be shredded. Then after this, we show that after it's A0 stabilized, eventually A1 will stabilize, and after this like this second layer never will be shredded, and so on. So we kind of showing that like kind of by induction that on n, then n many layers will never, after some points, will never be shredded, and then if some layer will never be shredded, this basically means that this layer is already correct about u. Yeah, and so this basically means that in limit, like we have this infinitely many layers that will never be shredded, and this basically gives us a stabilized model. Okay, so this is basically the concept.
May I ask something here? I'm not really a logician, and I'm absolutely not a recursion theorist, but I mean, I just know some words. I mean, is this have anything to do with what I've heard called, like, finite injury arguments, or is it more sophisticated or less sophisticated?
To be honest, the problem is I'm not computability theorist myself.
Okay, so it probably isn't.
It's a bit of a problem. So yeah, I was interested in the problem, and how the problem required me to do this. Unfortunately, I'm not that comfortable with this classification.
I mean, that means something very, very specific. I mean, everybody in the world has some notion of finding approximations and fiddling with it. But I mean, there are various sort of systematic protocols that have these names. And I was wondering if this was somehow, inspired by that. But it seems like
maybe it wasn't bad, because I see. Okay, I think I've seen like a couple of these constructions in computable model theory. So not like I'm completely unaware about this, but the problem I don't have like systematic education in this area,
right? And
I couldn't like tell.
Yeah, but you are a logician. I'm logic adjacent.
Finite injury, or how you call this, of infinite injury argument, or I'm not exactly sure what exactly this word means. But
computability adjacent.
Yeah, but certainly, of course, it's very much related to this kind of arguments in this computable model theory. So it should have some classification in this term, but I'm just not.
Can I add? I think that this whole idea of approximating a delta 2 set via finite objects, which are eventually settling down. It was introduced in an old paper of Putnam, and he called it trial and error predicates.
Oh, okay. So it does have a this is Podlack, you said?
No, Putnam, Hillary Putnam.
Okay. Oh, Hillary Putnam. Oh, I see. Okay.
Yeah.
Trial and error. All right, cool.
So it strikes me more like those than from a little bit that I know about priority arguments, sophisticated.
Yeah, priority. That's
Sophisticated,
another one of those words, right? Yeah, these are very, very systematized things that prove more than one theorem, right? So
yes.
Yeah.
but maybe it's also look, there's a little bit of everything. I mean, arguably the phrase Skolem function could have been thrown in at some point, right? I mean, it's a finite setting, right? So there's no choice issue, but you have something definable. You're taking the largest one to do something, and then. But anyway, seems very, very primal or whatever that. Primordial, not primal. Prototypical. Anyway, sorry to interrupt.
Yeah, no, but I already finished there. So this was basically.
I'll have to look at the paper.
Yeah, actually, the paper. I mean, it's not even that long, so I think it just.
I know. No, I know. I started looking at it, and then I decided I should just stop and go to the talk.
Yeah. Yeah. So okay. So let me give some closing remarks about what was actually achieved. Yeah. So. Okay, so first of all, the construction gives a bit more. So namely, in fact, so basically it's slightly modifying the construction, what it's possible to do with it. Okay, right. So the official theorem stated that any computably enumerable extension of T0 has a computable model. But in fact, any delta 2 so any model of T0 with delta 2 diagram has a computable. So any model of T0 with delta 2 elementary diagram has a computable copy. So this is what actually shows. So this first note. Second note, of course. So then, if you kind of go from this computably enumerable extensions to just arbitrary extensions, eventually it breaks apart. So namely, if you want interested in say arithmetical extensions, then they're not zero like this. So in fact, one could show that for no theory definition equivalent to Peano arithmetic, it could it will have computable models for all its arithmetical extensions. So basically, it's because of actually it's just quite easy modification of usual Tennenbaum's argument. So yeah, so basically one couldn't replace computable enumerable with arithmetical here. But actually, I don't know if one could replace it with some complexity from the levels of arithmetical hierarchy. Of course, I'm almost sure that probably one can do this, but yeah, this is open. So what I mean that finds theory Tn such that for any the definition equivalent to z plus minus n such that for any Pn extension of Tn, it will have a computable model. Okay, so this is an open problem. Yeah, and of course, probably the same could be like then like this delta 2 models will be replaced with delta n plus 1 models. Okay, so that's basically it. Yeah.
Okay, let's thank Fyodor. And we can open up for more questions if there are any.
Thank you, Fedor.
Oh, we don't do a preliminary clap in the seminar for a question?
It depends on the occasion.
Right, that's different protocols, different places.
Yeah.
Well, we may be exhausted.
Usually we do the usually I do the emoji, the clap emoji. Okay. So are there other questions? All right. Well, thanks again, Fedor.
Thank you.
I encourage everyone to. I think the paper is linked. The preprint to
Yeah.
the paper is linked on the New York Logic site. So in his abstract. So please do look for it there. And next week we will have a later start time. So we'll be starting at 7 p.m. New York time.
I do have a comment when you're done. I mean, I know I've
Sure.
asked a lot of questions, but I do have it's just this was such a good talk. I mean, I'm not a logician, but I'm considering myself set theory adjacent these days. That's what I do for a living. I teach set theory, and what little set theory I've actually done in research, half of it came out of coming to grips with that K long paper. Half was something else. And then much more recently, the other half of what you were talking about before it got technical and fiddly, and your own stuff, but like everything else was, I've been reading Torkel Franzen's book, Inexhaustibility, which I've been meaning to read for like 10 years. Right. And it's been like all about absolutely everything about that. So, I mean, this is sort of by way of explanation why I'm so glad I picked this talk. I mean, I would have watched the recording anyway, but hearing it live really helped me out. And if my former student was still here, Nathaniel, I'm sure it helped him out also. So it's just fortuitous.
I am still here. It was extremely interesting and kind of fortuitous because I was going over some old notes and seeing Tennenbaum's theorem recently. So thank you very much.
Yeah. Yeah, so thank you for kind words.
Okay, so yeah, let's thank Fedor again, and
Now we can clap.
and yeah, next week we'll have Cameron Williams here to talk about, and I have the title here, something about tightness, tightness in second order arithmetic, which is a notion from Visser and I think from Ali. And that talk will start a little bit later, or quite a bit later in the evening, New York time, so 7 p.m. New York time next week.